Welcome back to DeepRob for lecture 10. We'll go ahead and get started. Today's lecture is going to be a continuation of where we left off last week. So we're going to be talking more about some important kind of practical considerations to keep in mind when you go about training now your CNN architectures or your other neural net architectures. Before we get into the kind of technical content, just a couple administrative announcements. So with regards to Project 2, that has a deadline coming up this Thursday. So I hope everyone has started on that. The autograder, you should have gotten an email over the weekend. It went up online, and we've increased the submissions per day to 5 for this project just because I was so slow in getting the autograder implemented. So if you're having any challenges with the autograder, let me know. The other thing I want to mention is we've been updating the spec for the final project, and so that'll keep getting updated. I'm hoping to have your teams published and out to you no later than tomorrow. So maybe tonight, but probably tomorrow. And so be on the lookout for that. I think those are the only two administrative updates. Any questions administratively that I can answer? There was a quiz today. There will be a quiz Thursday, 2 quizzes next week. But yeah, okay. So if there's no questions, then we'll go ahead and get started. So what we're going to do to start with today is finish off a few subjects that we didn't have time for in last lecture. So in particular on the subject of regularization when we're training our neural networks. And then we'll get into the subjects that we have marked for today on this slide, which are the training dynamics, so how we schedule learning rates and hyperparameter optimization. And then we'll touch a little bit on model ensembling. So you'll recall that in the past lectures, we've talked now a fair amount about these different activation functions that we could potentially be using within our neural networks. But we settled generally on starting with ReLU as the first choice you should use in practice, and then potentially moving to some of these others kind of sparingly when you want to get just a marginal increase or try searching for a marginal increase in final performance. We also looked at then last time at the concept of data preprocessing by normalizing our data. So this related then to batch normalization, which we talked about a few lectures ago, and how that can help our neural networks to kind of have stable training, especially in the early stages of the training. But with then these different normalization techniques, there was that idea of weight initialization having potentially a big effect on our resulting final performance. And so in particular, we talked about how Xavier initialization or Keiming initialization is a good strategy to always start with for our fully connected and convolutional networks. And where we then left off, and we were just kind of starting to get into, was pointing out regularization. So at this point, once you've sort of set up your weight initialization, you've got your data preprocessed, you have your CNN architecture actually defined, what you might find is that you're overfitting to your data set. And so regularization then, just as how we talked about it in the context of fully connected just linear classifiers, regularization is the technique that's used to avoid overfitting. And so in the context of linear classifiers, what we looked at was by using an L2 regularizer or an L1 regularizer, which was an additional penalty that we would incorporate within our loss function. So we would have this data loss component, but then separately from that, we would also have this regularization component, which would try to incentivize, in the case of L2 and L1, the norm of our overall weight matrix, our weight parameters, being kind of constrained. And this idea, though, of regularization can be extended to additional forms where the general idea, though, is the same, of you're trying to avoid your model kind of becoming too complex, which that added complexity in the model is what's going to allow it to overfit to the data. So one common form of regularization within neural networks is what's called dropout. And so the idea in dropout is during the forward pass, you'll pick some random set of neurons within your network, and you'll actually just kind of set them to 0. So where you might have a fully connected, a series of fully connected layers in this neural network here, without dropout, right, you would just pass, feed forward through the network, calculate your hidden dimension at each stage, which would be these neuron activations, and keep going forward. During dropout, what you'll do is you'll randomly, with some probability, pick a few of these neurons in each layer, and you'll just automatically set their activations to 0, no matter what was coming as input. And the probability of dropping out one of these specific neurons is a hyperparameter. So in practice, picking 0.5, so just like a random toss of the coin, a 50% chance, is pretty common. And so what this looks like from an implementation standpoint, and so I think what you've probably started to see in Project 2, if you've gotten to this part, is in terms of how to implement it, would look something like what's shown in the code here. So what this is showing is during the training stage of a 2-layer fully connected network that is using dropout, so you calculate your, let's say your first hidden state by just taking like a ReLU activation on top of this linear layer, so the weight matrix multiplied by your inputs plus a bias term. And then you calculate separately this dropout tensor here, which is just a random tensor of the same shape as your hidden state, but then made to be a binary tensor by checking for each one of those random values, are they less than our hyperparameter p? So if they are less than your hyperparameter p, you're going to keep the activations, because this will be multiplied then element-wise by our activations. And for any of those random elements in this tensor that are greater than our probability p, we're going to be dropping out those corresponding neurons. So this element-wise multiplication is what, in practice, actually implements the dropout operation. And then you can keep going, continuing on into the network with like a second layer implemented in a similar fashion. And so that's how you implement it in practice. In terms of what it is the dropout is really trying to achieve, what it is going to do is it's going to try to sort of avoid your network parameters kind of co-adapting and overfitting to one another. So like if we take just as a conceptual example, like let's say that we have a classifier that's going to take in an image and maybe try and classify different robots that might be in the image. So maybe like a digit robot from Jesse Grizzle's lab. If we think about what some of the features might be that the neural network is hopefully going to learn, right? So maybe the network is going to hopefully learn to detect legs as being a feature indicative of digit because it's a bipedal robot. Digits usually are teal. They have those teal shells. So maybe identifying a teal color would be useful. Digit is not furry, but it does have motors. It does have a Velodyne sensor on its head. So these different features would be useful. And what dropout is going to do is randomly set some of these features as being not at all activated during training. So you're going to avoid allowing our final, let's say, layer, which has this dropout implemented, to sort of always look for legs and always look for a teal color. So it's sort of like maybe if it finds legs and a Velodyne and motors, like that's enough to still classify it as digit. It doesn't always have to find all of them. So dropout is trying to prevent some of this co-adaptation. That's one interpretation. Another interpretation of how dropout is successful at regularizing our model is that in effect what you're doing, because you have this randomness inserted into the network, is you're really training like every possible ensemble of networks where each of those within the ensemble is like a specific setting of that random dropout like tensor. So in a sense here, like every single binary mask that you could possibly sample from your distribution of binary masks fitting into the layers of the network is a separate model, and all of them are getting trained by training with dropout being used. And so because the number of possible masks that you can sample is so big, it's like you're ensembling over this huge number of possible models and benefiting from the power of ensembling, which is a concept in machine learning which we'll sort of touch on towards the end of the lecture if we have time. So that's like another interpretation of what dropout is doing. At test time, though, the important thing to realize is that if we were to still use dropout as we've defined it at test time, we'll actually now have random output, right? So depending on what your random binary mask is that was sampled when you try to evaluate the network during inference time, that's going to affect what the final output of your network might be. And so conceptually, this kind of seems at odds with what we want at test time, right? At test time, it seems like our model should sort of be stable. Like it should only depend on the image that it's trying to classify. It shouldn't have this like internal sense of randomness that's going to constantly be changing its potential answers if we ran it multiple times. So one way that we can try to avoid having that randomness affect the output at test time is to try and essentially like average out over the random variable, which in this case the random variable is the binary mask. So to do this averaging, what we're really describing as an expectation from probability theory. So if we imagine integrating over all the possible binary masks, then this would be a way to like ensure that our test time output is always the same. It doesn't depend on the randomness because you're sort of trying every possible random mask, seeing what the network outputs, And then this integral accounts for all of those possible outputs under the different binary masks. The problem with trying to actually do this in practice at test time is that it's not trivial to know how we would actually in closed form solve for this integral with a really complex neural network. So instead what's done in practice is we approximate this integral. So the idea here is what we're going to do is we're going to approximate this integral layer by layer, neuron by neuron, and use that approximation as our final output of the network with dropout for test time. So during training, we'll still apply dropout. We'll train the model. Hopefully, it will be regularized. But then at test time, we'll use this approximation. So how it is we'll implement the approximation is let's consider two cases. Let's first consider what this integral would be if in the case where we don't have any dropout. So if we just have a single layer that has two inputs like x and y and one output neuron A, the expected value according to this integral will just be the normal forward pass, because in this first case we're not using any dropout. So you would just take your W1, multiply it by x, and then add W2 and multiply it by y. Instead, if we imagine training this same layer but where we have the 50% dropout on each of these two parameters, instead if we were to now try and write out what this integral will be, well, we know that essentially the four possible settings are we're either going to keep both parameters, we'll drop out just W1, we'll drop out just W2, or the fourth option is we'll drop out both W1 and W2. And so because our sampling of the binary mask will be 50% for these two dropping outs, and they'll be independently sampled, the probability of each of those four settings is 25%. So if we write out what this integral will be, it'll be 0.25 times the output of the first setting, which is where we keep W1 and W2. We'll have plus 25% in the case where we dropped out just W2, plus 25% in the case where we dropped out both W1 and W2, plus 25% when we dropped out just W1. And then you add that all up, and what you'll find is that you get just 1/2 times your original, the original output if you hadn't used any dropout. So this intuition then is what leads to the test time implementation of dropout, which is at test time we actually don't use any random sampling. We'll just scale the output of our layer by the proportion of neurons that we were dropping out during training, and that's an approximation for this integral, which would be representing an elimination of all the randomness during test time. So to kind of put that more concretely into code in terms of how this is implemented, the test time pass, which is what you would run after you trained a network with dropout, would look something like this. So you'll have your two layers here, which were trained with dropout, where now we're just going to scale their outputs by the probability and not use any of those random samples during test time. So then putting that all together, the forward pass will have this random masking operation. The test time forward pass will just have scaling of the output. One kind of more common way that you'll see it implemented in practice is what's called inverted dropout. And so the idea here is that just to sort of make the test time pass a little bit more conceptually simple, we'll just move the scaling by the proportion of neurons that we're dropping out into the forward pass. So instead what we've done here is on our binary mask, we turn it into a floating point mask by just dividing by p. But in effect, this is the same thing. So it's just that now at test time, it looks like our normal test time pass. There's no dropout, there's no scaling. It's just forward, feeding forward the three layers in this case. But then at training time, we have both dropout and this scaling term incorporated. Okay, let me pause. Yeah, question. So the question was, is it not more representative to just zero out the gradients instead of applying dropout during training? Is that right? Interesting. So I wonder if you could implement something that is effectively like dropout with, that would be a form of regularization. So you're sort of adding stochasticity to the gradients. But that would be, I think, different than dropout, because that would just be affecting the backward pass. whereas dropout will affect both the forward pass and the backward pass. So when you calculate your gradients with dropout, the random binary mask that you're sampling for the forward time does also control which gradients can flow backwards. So what you're describing, I think, is a form of regularization, but it's just only like a backward pass form of dropout. Yeah. Yeah. Any other questions on dropout? Yeah. So the question was, how does like the idea of batch training or like batch-wise gradient descent affect our implementation of dropout? And so in this case, so dropout is defined here as like independent sampling across every neuron in your forward pass. So if you have multiple neurons for multiple batch elements, you'll sample a random binary mask element for those independently. So you'll have, so it might be that the same neuron across different images in your batch, sometimes they'll be turned off, sometimes they'll be left on with dropout. Mm-hmm. All right. So in terms of where dropout normally is used, you'll most commonly see it used just following a fully connected layer. And so in some sense, some intuition about why you'll see it there is because those fully connected layers tend to be where you have a lot of parameters in your overall network. And so that tends to be the portion of the network that's capable of overfitting very easily. So you want to sort of explicitly regularize your fully connected layers. You'll add dropout there. Notably, in the layers where you saw, or in the architectures where there was global average pooling, so like GoogleNet, ResNet, those global average pooling layers don't use any dropout. Okay, so kind of like trying to then wrap our heads around this idea of regularization, what we'll actually, if we try and like generalize this idea, what we can find is actually a pretty common pattern. So common across both batch normalization and dropout. And the idea is that during training, what most forms of regularization are really doing is they're adding randomness to the training process. So it's like we have our normal model, which is some function of the input, but now we're also making that a function of some random noise, some z. And then during test time, after we've trained with this regularization, this stochastic noise added, we're going to try and average out that randomness to sort of undo it in a way, or at least so that our test time output doesn't vary based on the randomness. It's just constant and it only depends on the image. So if we think back to batch normalization and how batch normalization fit into this pattern, during training where the stochasticity came into play, it was from how we sampled random batches. So you'll recall that with batch normalization, right, like the input to every layer now was going to be normalized by the batch statistics that we happen to sample. So every single, let's say, activation within our batch of samples for a given layer, the actual values will not just depend on the specific image that produced that element of the batch. They'll also depend on the remaining elements in your batch, which are randomly sampled. So you have like random noise being added during training in that form. And then during test time, because we used fixed statistics across the full training set, usually, that was our form of sort of like averaging out the randomness, right? So at test time with batch norm, we would always get just a single output. We wouldn't get different outputs because we're not doing any of that random sampling at test time. And so then dropout, like we just saw, also follows the same pattern. And most of these regularization techniques that we'll see coming up, you could also map back to the same pattern. So if you want to think about proposing new regularization techniques, maybe one useful approach is to kind of structure them or kind of frame them in this way, in terms of this pattern. So data augmentation is another technique which I would say falls into that category of regularization. And the idea of data augmentation is going to be something like this. So let's contrast data augmentation with what we would normally do during training, which is where we have some large labeled set of, let's say, images or inputs to our model. And what we do is we take those images, we feed them into our neural network, and then we compare the output of our network with the ground truth label, and then that's our training signal, is that loss that's defined between the neural network's decision and the ground truth network. What data augmentation is going to do is it's going to first insert some like known pre-computed transform on the image so that the label for the image will stay the same. But now at a pixel level, we have this new transformed input to our neural network. And so in effect, what data augmentation can do is it can be a source of noise during training. And also what it can do is it can effectively increase your training set size. So, and it can do this by a substantial amount. Like you can have in effect training size that's maybe like an order of magnitude or multiple orders of magnitude larger than what you actually have if you use enough data augmentation. And let me close this. Okay. So let's look now at a few forms of data augmentation that are pretty commonly used. So the first would be flipping your image. So in this case, you can see on the left-hand side, we have this image of our pretzel bag, which we want our robot to go and grab for us as a snack. And then on the right-hand side, we just horizontally flip every pixel in the image. So this still represents a pretzel bag visually. We would still want our CNN to detect this pretzel bag. But notably, right, like there are features now that are changed. So like, for example, the Hershey's label, if you kind of can make it out in this kind of scrunched up version, is now sort of printed incorrectly. So it might be the case that our robot would never actually see this like horizontally flipped or like incorrectly printed Hershey's label. But this can still be useful for training because now like we could still detect like these pretzel features or some of the other characteristics on this bag, which might be useful for the robot. Also, though, it might be the case that maybe our robot does at some point see a misprinted pretzel bag, and we would still want it to bring that to us as a snack. So incorporating data augmentation can still kind of cover some of those edge cases. Having said that, though, in some sense, what you're doing when you pick which data augmentation techniques to use is you're sort of expanding your training set size, but you're also kind of picking like what portions of the possible overall image space are valid and you want your model to think about. So vertical flips, for example, have a pretty big ramification on like that portion of image space because let's say that we wanted our model to detect digit, like the digit robot. If you vertically flip images of the digit robot now, it's going to be like standing on a sort of ceiling visually. That's something that you probably will never actually see in the wild. So those kind of choices about which data augmentations you choose to include or not include will have ramifications sort of on what distribution of data you think your model will see. So it might not make sense, basically, to sometimes do a vertical flip. So another common technique for data augmentation is randomly cropping and randomly scaling the image. So this was used, for example, by the ResNet architecture. So what you'll do during training is you'll pick basically like some random, let's say size L from some constrained size relating to one of the dimensions of the image. You'll resize the training image according to that random size that you pick, and then you'll crop a square patch from that kind of like scaled version of the image, and then rescale it to be a constant input size, so like 224 by 224. And then you'll feed that into the network. So during training, you would keep randomly cropping, randomly sampling these subcrops from the image, and use the same label. So the idea is that each of these crops, like in the case of this pretzel bag, would still have enough features that you would want your model to detect it as a pretzel bag if you're doing image classification. So you wouldn't crop down to such a portion of the image where like there's no features relating to the pretzel bag. So you wouldn't want to crop down to like maybe where there's just like images or just pixels on the grate, like the surface, or just the wall. You would still want your classifier to be able to have enough features to detect that there is a pretzel bag. At test time, then, what you do to try and sort of get rid of this randomness that we use during training is you can now like take a set of crops from your test time image, feed all of them through your network, and then you would average, let's say, the scores over all of the different categories that your classifier might be trying to classify, and use that as the final model's decision. So in the case of ResNet, they would resize the image at these 5 discrete like resize values. They would then take 10 crops for each of those scales, and then average the final scores across all the categories for all of those images. So another slightly more complex version of data augmentation then is what we call color jitter. So in a simple case, what this could look like is you just randomly change the brightness and the contrast in your image. So if I can find my cursor. So like in this case, right, so you might have like your original image of the pretzel bag, and then after maybe you like slightly increase the contrast and slightly reduce the brightness, and you'll get this new version. So it still represents a pretzel bag, we still want our model to classify it as a pretzel bag, but we never saw this exact image on the right when we were collecting our data. A more complex implementation of color jitter, which you'll also see in practice, is where you'll use principal component analysis. So what you would do is you would take every single pixel in your entire training set, and you would treat every pixel like a three-dimensional vector somewhere in the RGB dimensions. You would run PCA on that full data set, and then you would sample color jitters for some new image during training based on steps along those principal components that PCA gives you. And so in some sense now it's like this distribution of color jitter that you're gonna get is now based on the data set. So you're sort of like hopefully changing the color statistics for a given training image according to the data that you see on distribution. So it can be like a more informed maybe way of applying color jitter. So this form, for example, was used like in AlexNet and ResNet and a number of other state-of-the-art architectures. And we're gonna kind of keep going. So there's like quite a few forms of data augmentation. So like those are all isolated forms, right? So you could do horizontal flipping, you could do vertical flipping maybe, you could do color jitter, but also you could compose them, right? So maybe you could first horizontally flip and then add color jitter. And so rand augment was proposed as a fashion of applying this like composition of data augmentation transforms. So they proposed a set of geometric transforms. You could like rotate images, translate, shear the image, and then also affect the color statistics. So you could like sharpen, contrast, change the brightness, change the color. And then it would do this in a composed fashion. So what this might look like is you would sort of pick like a magnitude or like how extreme you want each of these transforms to be applied. And then it would go through maybe first do a shearing transform and then affect the contrast. And so in this example, what's being shown is like you could pick this hyperparameter that would control, in this case, the kind of like the magnitude of the shearing operation. So if you increase the magnitude, the possible shears that you can apply to your images during this augmentation is sort of more substantial. It's more extreme. So just in terms of like choosing which transforms you would include in your composition is one hyperparameter. But then even internally, you have this like continuous hyperparameter, which is the magnitude, right? Because it's kind of like a sliding scale hyperparameter. You could increase it or decrease it. It's not just discrete of adding it or removing it. So yeah, so rand augment is a way of composing then our transformations, and also by doing it randomly. So I think if we go back to like this pseudocode, let's see. So like I'll even point out that it's, so within like this rough pseudocode for how you could implement it, it's not that you would always apply all of these transforms. Like sometimes you could randomly turn off a few of them, but keep others. So there's additional randomness added there in that form of data augmentation. So to summarize this idea of data augmentation, it's really essentially always used when you're going to train a neural network. It's very highly recommended. And in some sense, what you're doing is you're encoding what you want your model to be invariant to. So in the case of horizontally flipping, what you're encoding is you want your model to be invariant in its classification decisions to what the like relative along the vertical axis of the image pixels, what you want your classification decisions to be invariant to. So it is worth thinking about, because like we talked about in the case of like a vertical flip, in some cases, if you're trying to detect things that are dependent on its vertical orientation, that might actually not be beneficial incorporating. So you can put some thought into which data augmentation approaches you use, and it will depend on the specific problem that's at hand. But it is generally recommended, and you'll see it used, I would say, in essentially every implementation of a neural network. Yep. Yeah, really interesting question. So the question was like, can you implement data augmentation as like a class-dependent operation? So for example, so the example that was given was, it was a basket, like you never see a basketball hoop upside down, so you might not want to vertically flip basketball hoop pictures. And then I forgot what the first example you but a water bottle you might see upside down. Yeah, that's a perfect example of a case where yes, you can do it class dependent. It gets a little bit more complex to implement, like because you're like when you actually like, are sampling batches and then applying your augmentation, you'll want to have like a control flow that depends on what the class is. But yeah, you'll see that done in practice. The question was about scaling, because we mentioned like you still want there to be like enough features in your cropped version of the image so that you would still reasonably expect your classifier to detect or to classify the image as whatever the image is labeled as. So to some extent you can tune it. So it is a hyperparameter. So you could go too extreme to the point where, like, if you're even cropping down to like a single pixel, right? At that point, you've lost so much information that you really wouldn't expect a model to be able to classify. Having said that, it actually turns out that even just like as a source of noise, it's sort of okay, or even maybe recommended that like you pick your scale so that there actually are some cases where there's not really enough features to detect, like let's say the pretzel bag. But it's kind of a tuning question. So as a general rule, though, like you still want there to be enough features on average that you could expect a classifier to classify the image according to its label. But having noise in that form, like you're describing, can be beneficial by itself. Yeah. And actually, we'll see some examples more explicitly of how adding noise in the sort of labeling, which is kind of what that cropping effect we'll get to, is actually used. Okay, so we've now talked about dropout as a form of regularization, batch normalization from a few lectures ago, and now data augmentation. And within data augmentation, obviously there was that whole set, and there's even more that we didn't kind of touch on, where the general pattern, right, is we're going to add randomness during training, and then at test time we're sort of marginalizing out, we're integrating out that randomness. So another version of regularization similar to dropout is what's called drop connect. So actually our example, like our worked out example of dropout was really drop connect, where we, instead of zeroing out specific neurons, the activations of specific neurons, you zero out specific weights during the forward pass. So when we worked through that example, it was really kind of a drop connect example. In practice, you see dropout used much more than drop connect, but this is one to be aware of. Another kind of fascinating one is what's called fractional pooling. So the idea here is when you have pooling layers, so let's take like a max pooling layer. The way we've introduced max pooling up to this point is you would use that fixed kernel size for the windows that it would take a max over, right? So maybe like a 2x2 max pool with a stride of 2. Well, in fractional pooling, what you'll do is you'll randomize the window size. So on some images during the forward pass, during training, you might still have a window size that's 2x2. But then in other cases within that same image, you might have a window size that's 2x1. And then in other cases of the image, you might have a window size, like where is it, down here, that's 1x2. So what you're sort of doing is trying to force the network to be invariant to the specific kind of like edge pixels within your window, based on your window size. Question? I believe that the sampling here is chosen so that it still ensures the same output size. But that is a really good point. I would say, yeah, if you look into how it's implemented in practice, I think you'll find how it is that they can fix that. I believe that's how they ensured that, like when they're sampling these different dimensions, I believe that they do ensure that the final output is the same size. It's possible though that what they could do also is like add padding to also fix that. I don't remember how this paper implements it, but there's a few ways. So if you're interested in those details, yeah, refer to the paper. And so in effect, what this is doing on average, it's worth pointing out, is sort of like changing your effective window size to maybe be like a fraction. So instead of being like discrete, like 2x2, maybe now your effective window size is really like 2.5. And so fractional pooling. Another one which is kind of similar to dropout, except now it's at the block scale, is what's called stochastic depth. So in particular with residual networks is where you will see this implemented. The idea is, so as like a quick refresher, you'll recall that what residual networks were built on were these residual blocks where you would have a skip connection, right, this residual connection, which would be an element-wise addition operation based on the output from your residual block and the input to the residual block. So what the intuition then here is you could say, well, because I have that residual connection, I could actually turn off the entire block and still run my full network. Like all the input and output sizes across the overall network will still be kind of like, they'll still be valid. Like you could still actually call the network in a forward pass and you won't get any like runtime errors based on sizing. And so what stochastic depth then decides to do is, like, let's have a hyperparameter that picks with some frequency, turning off the internal portion of each of these residual blocks, but just keep the residual connection. And so it turns out that this actually can be beneficial. And so increasingly, like as time is going on, you're seeing it. So like these are more common, more recent papers. You're seeing it used more and more, and it can improve the final, like your final model performance. And so usually what you'll see implemented with this is the rate at which you drop out residual blocks will be higher in the earlier portions of the network, and then lower in the later portions of the network, if I'm recalling correctly. And so that's kind of an interesting, that's really interesting, right? I mean, all of these data augmentation, all these regularization approaches, they're all to some extent a little bit kind of counterintuitive, right? Like you would sort of think that you would want your model to, your architecture to be fixed during training, that it would benefit from sort of being stable. And yet it turns out that having this source of noise, even at the block level, right? Because remember, like if you look at some of like those Chris Olah blogs where they go and introspect the model, a lot of these layers are learning like increasingly high-level features to detect increasingly high-level features. So the idea that you could remove an entire block and have, which is maybe detecting like at the level of cats and dogs or cars or windows, and your network can still perform classification tasks to a high degree is really fascinating. So stochastic depth. Another one, so at the pixel level, is what's called cutout. So the idea here is you'll pick random image regions in your input image, and you'll either set them to some constant, like you'll set them all to 0, which is what's sort of being shown in this upper region, or you could set those entire regions to just random noise. So like these pixels here, for example, are like being set to just some randomly sampled noise. This also goes by the name of random erasing. So then at test time, you could potentially like perform that same operation, or at test time, you could even just run your regular image without any of the random erasing being applied. Another also very counterintuitive one is what's called mix-up. So here what you do is you sample some probability, and then based on that probability, you combine two different images from different classes. So we have like our image of a pretzel bag, and then maybe we have some other class which we're trying to classify, so maybe like a class of a robot. So here we have our fetch robot. So you would randomly sample some probability value. So let's say like you'd sample 60%. And that would then indicate that, okay, I'm going to take like 60, like with alpha blending, I'll take 60% of the intensity of the pretzel bag and combine it with then the remaining 40% out of a whole 100% of the pixel intensity from the robot image. And then you get this mixed, right, this kind of like blended image, which is then used as input to your network. Correspondingly, what you'll do, and this is the first case that we've seen of this with regularization, is you'll actually change your labels based on your random sampling. So instead of having this be labeled as a pretzel image, instead we'll have it be labeled as like sort of 60% pretzel and 40% robot. So you would want your classifier in this case to have scores that match this target distribution. So instead of like a one-hot label distribution, now it's this continuous distribution across the classes based on your sampling. It turns out, I will point out, it turns out that like the specific distributions that you use for the sampling of your blending hyperparameter do actually control the effectiveness of this. So for a lot of these data augmentation and regularization techniques, they're sort of like, they're useful, but they still depend on the hyperparameter choices. So every time you add one of these, you're increasing your search space of hyperparameters. And in some cases, like mix-up is one case where it can sort of have like its usefulness can have a big effect on the hyperparameters. Other cases, like horizontal flips, for example, are essentially always useful. But in some of these other ones, like your hyperparameter choices can really affect how useful they are. Yeah, so the question was like, in the real world, would we ever expect to see images that look like this? Or is this just something kind of counterintuitive that happens to work well with neural networks? I think there's sort of two answers on that. One is, I do think it's sort of something counterintuitive that just happens to work really well in practice with the neural networks that you should be aware of and you should use in practice. At the same time, I do think there are interesting phenomenon that can happen. So for example, like reflections. So like even like reflections from this whiteboard, it's not a mirror. Like it's not reflecting all of the light rays that are passing from maybe like the ceiling to my eye, but it's sort of blending them with the actual texture of the whiteboard. So there are cases and like even like glass is another case where you kind of get partial, like a partial reflection, but also partial transparency through. So I do think for our robots, like there are cases where this actually could be observed. But what we would probably care more about is detecting why there's this weird, like transparent or reflective phenomenon in the first place. No, exactly, right. So yeah, all of these techniques that I'm talking about here, they are all beneficial for just the final, once you've evaluated your model on the test set, which doesn't include these mixed up or like randomly cropped or so forth images. It improves the final like top 5 or top 1 accuracy on those cases. Yeah. Yeah, thanks. I forgot to point that out. That's a nice benefit from the standpoint of effectively increasing your training set size that data augmentation gives you. A nice benefit with data augmentation is it does not require you to increase your disk space. So you can just keep whatever your annotated image set size was for training, you can just keep that on disk. And then at test time, when you sample a batch from that, you can apply these augmentation techniques using compute. So it's kind of an interesting case. So you could, if you wanted to, you could apply them all, or I mean, we couldn't apply them all because a lot of them are continuous. So there's like an infinite range of values we could get. But you could, if you wanted, sort of like apply some of them and then resave those augmented images to disk. But there's really no reason to do that. Instead, because these are all very cheap to compute on the fly. So instead, you'll sort of randomly sample a batch from the images that you labeled, which are stored on disk, apply some augmentation, feed them to the network, backprop with those, and then you'll throw those augmented images away. They'll just be erased, and you'll go and sample a new batch. Yeah. I will point out, it's a really, like this is a really interesting case of like the, like this idea of that you can apply these augmented images is an interesting case of the, what's called the memory computation duality. Just for those maybe like computer science oriented minds that are interested in that, you can look it up and read offline. It's kind of an interesting concept. So we had mix up. Another related idea is what's called cut mix. So here, instead of blending images with alpha blending, instead what we do is like, let's say we take our pretzel bag image, and then we take our robot image, and then we just sort of rescale the robot image and just stick it somewhere randomly in the pretzel bag image. So now you have this sort of weird, like, this weird hybrid image that has features of both classes. And correspondingly, you might say, okay, well, 60% of the overall pixels from this resulting image are from the pretzel bag, 40% of the pixels in the overall image are from the robot. So I want my target distribution to now be 60% pretzel, 40% robot. So again, even in this case, the top 1 accuracy is improved by incorporating this during training. I'll also point out that generally speaking, in practice for all these cases, you wouldn't sort of pick one and always use it. So it's not like we would pick cut mix and then just train on cut mixed images. You would use cut mix, you'd use dropout, use batch normalization, you'd use stochastic depth, and then for all of like the image level augmentations, you would randomly apply some of them or not some of them with probabilistically. So maybe like 10% of the time you would do cut mix, and 10% of the time you would do color jitter. So then between the two, it ends up being like 1% of the time you would do both together. And then also some of the time you'll just train on your regular non-augmented training images. So you're going to be mixing all of these together. It's not like you're always going to pick cut mix and always do this, because that would be then changing the distribution of your data set to like these weird like combined images, which is not what we want our model to ultimately perform well on. Okay, another interesting case of regularization where we're going to change the labels is what's called label smoothing. This is an interesting one. There is like a little bit of intuition about why this one might work. So let's say that we're training our model to do classification. We have our pretzel bag again. the standard training might have a label that's like a one-hot distribution. So you'll have like that this is a pretzel bag with 100% certainty, and then it's definitely not a robot. It's definitely not our sugar box from like our props data set. What label smoothing is going to do is say, leave the image the same, so don't augment the pixels at all, but just change what the label is and say that really what you want your classifier to do is predict 90% pretzel bag and then have some non-zero percentage score for the robot and the sugar class, the incorrect classes. So the way to actually implement this is like according to this equation where you pick then like this epsilon, which controls how much score essentially you want your model to predict on the incorrect classes. And this is used specifically for certain losses where if you have noise in your labels, so if you actually have, if maybe you have some cases in your training set where images of pretzels are incorrectly labeled as robots, with like a cross entropy loss, which is going to try to force your classifier to match the labeled distribution. If you have those one-hot distributions, you can have huge penalties for noise in your labels. So this label smoothing can reduce very drastically the penalty. And so probably that's why it's beneficial. For more details, we link to the paper where this is proposed down here. But that's regularization. So those are just a sampling of techniques within regularization. As you probably are getting the sense, proposing techniques for regularization is itself an area where you can contribute to the field. And so consequently, there are many regularization papers focused on developing these new techniques. But as a summary of what we've looked at, the techniques then that we've seen are shown here. And the main takeaways are, so for fully connected layers, dropout is a good technique to avoid those co-adaptation of their parameters. Data augmentation is always going to be used in some form, and then it's really just a matter of how many of those that we looked at you'll use or which combinations you'll use for your data. Using batch norm is very common and highly recommended for convolutional neural networks. Typically, it's not used for vision transformers, which we'll talk about in the seminar style section of the course. And then these other techniques that we looked at, you can try them and sort of add them to your augmentation routine, but they'll probably just give you marginal benefits. None of these that we've talked about are going to like make or break your model's performance. They'll give you some increase in performance, but they're sort of something to try after you know your model is working to try and improve the performance. Yeah. Okay. So that gets us to where we were supposed to end last lecture. And now today what we're going to talk about are additional things to consider when training neural networks. And in particular now what we're going to look at are what we could call like things to consider as the training is happening. So learning rate schedules and hyperparameterization. Okay. So we just looked at that. Okay. So learning rate schedules. So with the different forms of optimization that we have talked about so far in this class, so like stochastic gradient descent or maybe doing ADAM optimization or ADAGRAD, all of them depend on learning rate as a hyperparameter. And as a general rule of thumb, the actual scale of your learning rates in relation to the combined like parameter initialization, data set, optimizer, let's say regularization space, matters. So how large your learning rate is versus how small your learning rate is can drastically affect what the convergence properties of your algorithm is using these optimizers with neural networks. And in particular, as another kind of rule of thumb, what this figure is showing is sort of what to expect or how to interpret the loss that you're observing during training based on its convergence properties in relation to the size of your initial learning rate. So if your learning rate initially is sort of too big, what you'll almost certainly find is your model will diverge in loss. So you'll find probably even more rapidly than what's shown here. So what this plot is showing is on the x-axis, that's like basically training steps. So one epoch would be you've gone through like all the images in your training set. So this is as x goes forward, you're training longer. And then the y-axis here is showing your model's loss. So high loss is bad. So with too large of a learning rate, typically what will happen is your model will diverge. The loss will sort of explode in value. It will increase very, very fast. With a learning rate that is sort of maybe still too high, you might expect the loss to drop very, very quickly as a consequence of having this high learning rate, but then it'll sort of plateau above what a better tuned learning rate will give you. So instead, the sort of optimal learning rate, which maybe will be sort of in between too high and too low, is one that has that nice exponential decrease very quickly in terms of loss, and then plateaus or starts to converge very low to the sort of absolute, to it like an absolute minimum of loss, like a global minimum of the loss. And then too low of a learning rate is one where you might see like a decrease initially that's much slower than exponential, maybe even like a linear decrease, and then it just takes a very, very, very long time to actually converge. So interpreting these sort of loss plots in this framework can be beneficial as you try to tune your initial learning rate. And so we sort of step through this, I think, like in terms of which of these is the best to use. Well, sort of all of them are potentially good to use if you sort of either have enough time, except for the very high learning rate. That one will diverge and not ever come back. But what maybe we want to do is like start with a very high learning rate so that we hopefully get like this very fast decrease, this like exponentially fast decrease. And then maybe to avoid getting stuck in these plateaus, sort of like decrease the learning rate with some step over time, like actually decay the learning rate over time. And so in practice, this is what's used to a great effect. So this idea of stepping of the learning rate will produce loss plots that look generally something like what's shown here. So in a lot of literature, you'll see loss plots that will look like something like this, where you'll see these big steps down in loss at sort of seemingly discrete time steps. And what those indicate is that very likely, at least, the actual learning rate at those specific time steps during training was decreased by some factor. So usually you might see like a factor of 10 decrease at specific epochs during training. And so at those specific epochs, the hyperparameter was chosen such that the actual learning rate, would be basically multiplied by some factor, like multiplied by 0.1 or maybe 0.05 or something like that. And then just to point out, though, keep in mind, this is another hyperparameter. So this is like, in practice, this is used, and this is what's generally observed. But it's not obvious how you should decay your learning rate, either in magnitude or in terms of the frequency during training. So that's something you have to tune. You have to actually, like through trial and error, sort of figure out what works well for your particular model architecture, your data set, your optimizer, all the other hyperparameters that you've chosen. So don't feel like there's like one correct factor to scale the learning rate by, or one correct step size during training. It's tuned. So a constant step size is one way to do it. In addition, though, there are other forms of learning rate decay. So instead, what you could do is use like a cosine decay, where what you'll do here is you'll pick an initial learning rate, which would be like your alpha naught, alpha 0, and then you'll pick a total number of training steps that you intend to take. And then according to this, according to the cosine function, then you'll use the cosine function, basically kind of scaled based on that total number of training steps, to control what your learning rate decay schedule looks like. And typically with a cosine learning rate decay, you'll see loss plots now that look something like this. So notably, this scaled version of cosine is starting at 1. So that's going to just be giving you like alpha naught, and then it's going to go all the way down to 0. So at the very last training step, according to your total number of training steps, this capital T, at that point then your training will sort of be stopped by the fact that your learning rate will then be 0. So you tend to see sort of smoother decreases in the loss with this form of learning rate decay. You don't see those giant steps because we're not taking discrete, we're not taking like decay steps at discrete times during training. It's a continually decaying learning rate. Another choice is a linear learning rate, right? So this is like a little bit more conceptually simple than like a cosine decay or a stepwise scalar decay. So here the idea is just once again, like you'll set like an initial learning rate and then some total number of training steps that you intend to take. And throughout those total number of training steps, the decay of the learning rate is just going to be according to a linear schedule. And one that you'll see sometimes in the transformer architectures, but you don't see it, I would say, really used outside of that, is an inverse square root decay. So I just want to point out, I'm just pointing this one out just because you'll potentially see it during transformer literature. But the one that's probably important to start with is just a constant learning rate. So for the purposes of setting up your network, it's always good to start simple before adding in like really complex augmentation or complex learning rate schedules, because you're like all of these techniques that we're talking about, they're really ways to optimize your performance. But you should expect with a constant learning rate and just a well-tuned initial learning rate to still achieve like, we'll say like reasonable performance on your given problem that you're looking for before turning to these learning rate schedules. So always sort of start with a learning rate that's constant and just try tuning the initial value and then try adding in maybe like the cosine, like a cosine decay to try and just like optimize the model's performance a little bit more. In addition, what these decays generally are useful for is when you're ready to train your model for a really, really long time. And by then you'll want your initial learning rate to be well tuned. So once again, so like the advice is tune your initial learning rate with a constant learning rate. And then once you're ready to let the training run, like probably even beyond overnight, maybe like a week-long training or a month-long training, something like that, then you would incorporate learning rate decay as a way to really squeeze out all the performance you can get. Yeah. Okay, so another technique that's beneficial now that we're actually training our networks is what's called early stopping. So the idea here is it's very possible, now that we have all of this complex data augmentation and these really large neural networks, to actually maybe overfit our data, even with the data augmentation regularization. So what early stopping is going to try and do is it's going to sort of evaluate both the training loss or the training accuracy and the validation accuracy throughout training. And if it starts to see that the training loss is like kind of like greatly exceeding the validation loss or the validation accuracy, then it's going to decide to stop training because that's an indicator that your model is starting to overfit. So you'll sort of like keep evaluating these as you're training, and then once you see some divergence where your training loss keeps improving but your validation loss is plateaued or maybe even started to decrease, then you'll stop, you'll save the model at that point, like you'll save the parameters of the model at that point, and you'll say, okay, training's done, this is the best model that I'm going to get. Because if you were to just be looking at the training accuracy, you would just keep saying, oh my God, my model's getting better and better and better, and I have nothing to worry about. But it's only by looking then at the validation accuracy, which once again is like that held out set of images and labels, or at least the held out set of inputs and outputs. It's only from looking at that you're really going to get a measurement of what to expect your model performing out in the wild. So yeah, early stopping is common. Okay, let me pause and see, so from like early stopping or the learning rate schedules, if I can take any questions or clarify anything about those before we move on to how it is we can choose our hyperparameters. And we have so many hyperparameters to choose. Okay. So yeah, so now there's like this question because we've introduced a lot of hyperparameters. Right, like the CNN architecture obviously is itself a hyperparameter. All of our choices about which data augmentations or which forms of regularization we use are hyperparameters. But then even internally to those specific data augmentation techniques or those specific regularization techniques, there were those tunable hyperparameters like the strength of the regularization, or like the dropout parameter in dropout, or the magnitude in the case of that shearing transformation. So how do we choose these? Well, one approach, which is what we've been doing in the projects, is what you could call grid search. And so the idea here is just for every single possible hyperparameter that can take on a different value, you'll enumerate some set of values that you want to search for each of those hyperparameters. So like maybe for weight decay, you would say, I want to consider like 1 times 10 to the negative 4, 1 times 10 to the negative 3, 1 times 10 to the negative 2, 1 times 10 to the negative 1. And once you've enumerated for each of your hyperparameters the possible values you want to search, you'll then try every possible combination. So you would try like 1 10 to the negative 4 for weight decay and 1 10 to the negative 4 for learning rate. You would run your full training process, then you'd evaluate on the held out validation set, and you'd have like a measure of that model. Then you would take the same model, so control for the architecture, but then you would take like a weight decay of still 1 times 10 to the negative 4, but a learning rate of 1 times 10 to the negative 3, and do the same thing. You'd like train across your data set, but holding everything else constant, evaluate the accuracy on the validation set, and now you'd say like, okay, which of those two hyperparameters was better? Was it better to say 1 times 10 to the negative 4 for weight decay and 1 times 10 to the negative 4 for learning rate, or 1 times 10 to the negative 4 for weight decay and 1 times 10 to the negative 3 for learning rate? So right off the bat, right, you can see how trying every possible combination in this grid search approach is going to be pretty hard, because we're going to have to train a different model for every single possible choice. So in general, if we say that we have, let's say that we have like n different like hyperparameters that we were going to consider different values for, and for each of those we have k different discrete values that we want to try. In total, you're going to have to train and then evaluate your model k to the power of n times. So in this simple case, right, it's not too bad. It's 4 times 4. But in the case of where you're adding different data augmentations and you're adding potentially even different neural network architectures, which is a hyperparameter that some people like to search over, this explodes, and it's not really feasible to try all of them. But for the purposes of like, once you're pretty sure about a CNN architecture and you kind of cull down the list to just like learning rate and maybe a few regularization hyperparameters, then grid search is one that you could implement in practice. So don't write off grid search. It is good to still use in practice, but if you want to do really big searches over like a large set of hyperparameters, it's probably not going to work. Instead, what you can do is you can try random search. So the idea with random search is you're gonna, instead of trying every possible random combination, or every single combination of a discrete set of hyperparameters, you'll pick a distribution for the different hyperparameters you're going to try and tune, and then you'll randomly sample from those distributions, trying random combinations from each. And in practice, what's typically found, and we'll show some results to kind of motivate this, but in practice, small changes in these hyperparameter values tend not to make a very big difference. So what you'll typically see both in grid search and in random search is we're describing the hyperparameters in like a log linear scale. So we're taking linear steps, like powers of 10 steps, because what we find in practice is that it requires really big changes in the hyperparameter values to have correspondingly big changes in model performance. At least for like learning rate, weight decay, at least for those, right? On things like dropout, it is itself defined as a linear scale. It's between 0 and 1. But that's why we have like a log uniform distribution here. It's because typically small changes in these learning rate and weight decays aren't expected to have a big impact on the final model's accuracy. So in terms of why, like an additional reason why random search can sometimes be better than grid search, there's this interesting concept which was presented in this paper here, which is, let's just like a conceptual kind of like a thought experiment, let's say that we have 2 hyperparameters that we're trying to search over. And let's say, just for the sake of argument, that one of them, maybe the one that in each of these plots is shown on the horizontal axis, is very unimportant. So in other words, like changing along the horizontal axis tends not to affect the model performance at all. In contrast, let's say that our second hyperparameter, which is on the vertical axis of the 2 plots, is, oh, did I mess that up? I'm sorry. The horizontal axis is the important hyperparameter, and the vertical axis is the unimportant parameter. In the case of grid search, what's going to happen is all the points along this important hyperparameter, so all the points along the vertical axis, are constrained to these kind of columns, right? They're constrained to just like these 3 possible values, just as a function of how grid search is defined. In contrast, if we were applying random search over these 2 hyperparameters, random search no longer is constrained to those 3 columns. Instead, every time you pick a different combination of like a random value on the x and the y, you're sort of sampling implicitly somewhere that's kind of continuous along this important hyperparameter. So you'll potentially be able to find regions of the important hyperparameter that are very beneficial, and you don't even really need to worry about the unimportant hyperparameter, because in some sense it's like kind of like marginalized implicitly out. So that's another benefit of random search, is it can potentially aid in cases where you have like some hyperparameters are very important and others are not important over grid search. In practice, this is an interesting result that was produced by the former instructor of this course. So Professor Justin Johnson worked on this project where they tried looking at essentially like what is the effect of some of these hyperparameters on model performance for image classification. So what they were looking at here is for 3 different architectures. So there was like some vanilla CNN, a ResNet architecture, and a darts architecture. Every point then within these plots is a different model trained according to the then hyperparameters at that model's like XY position. So just think like every single model, every single point that has a color was a different training and then evaluation of the model. The color of each of these points corresponds to the resulting accuracy that resulted from the model trained with those hyperparameters. And the takeaways then are, even across these different architectures, the general performance, for one thing, follows sort of a structure, because you have these bands, these sort of regions, where's my cursor? Like these regions in hyperparameter space where the final accuracy stays relatively constant, even if you just make small changes to the hyperparameter values. So in one sense, there's structure in this like overall hyperparameter model performance space. And then at the same time, the takeaway is that like very small changes in the hyperparameter choices tends not to have very extreme effects on the model's classification performance. So those are the 2 main takeaways to take from this. Yeah, and then I'll also point out that this is being shown on a log scale. So like the small changes on a log scale are actually even bigger than visually they might seem. Okay, so that's all good if we can try running these models with like an exhaustive grid search, or with random search running like over the course of weeks and days or maybe months. But in the case where we don't have like a lot of computing power to support this search, we should think about other ways where we could still choose hyperparameters effectively. So the first thing to always do when you set up a neural network for training is to just do a sanity check that your feed forward and your feed backward pipelines are set up correctly. So the ways you can do that, sometimes you can have intuition about, based on like the definition of your loss, right? So the same way we saw for softmax, that we could actually by hand derive what the expected value for softmax would be if it was given sort of random input, and check then that the output loss we see for a randomized initialization is close to that expected value. So you can do that sometimes. The other things you can do, though, are just to make sure that your gradients are non-zero. Like that's a very simple sanity check. You can make sure that your outputs are changing with changing inputs. So you can just sort of do like some initial sanity checks on your feed forward and feed backward process. At that point, the second thing to always try doing, I would recommend, is to try overfitting your model to some small amount of data. So take just like a small collection of mini batches from your overall training set, fix those. So maybe take like 5 mini batches, hold them constant, and see if your model can overfit to those batches. And by overfit, we mean like even memorize, like perfectly predict the labels for all the images in those batches. And again, this is a really good sanity check just to make sure that like that feed forward, feed backward is working. Your loss is set up to sort of match what your labels on the data are. And also you can start to tune your learning rate in this way, because it should be able to overfit fairly quickly. Like with fewer than, let's say, like 1,000 optimization steps, you'll generally want your model to overfit on a small amount of data. So this is all something you can do very quickly. You might not even, depending on your network architecture, you maybe even could do these first 2 without really a GPU. You might still want a GPU though. So that's the second thing. After that, then what you want to do is start tuning just your initial learning rate. And you want to look for a learning rate such that you see that really fast, like sort of exponential drop in loss on the first, let's say 100, first 1,000 steps of training. And so just like this initial learning rate tuning is again something that you can do without needing to run like an exhaustive hyperparameter search. From there then, you probably will want to do more of a grid search on hyperparameters, where maybe you start with just some kind of good like rule of thumb hyperparameters choices to start with. So you'll usually see values in this range chosen for learning rates when you're training with Atom. So sort of picking like what's usually used for other networks is a good starting point for your hyperparameter search. And then at that point, yeah, you can actually maybe spend like a few hours of training. At that point, then maybe what you can start to do is like refine your grid. So you can kind of like iteratively focus in your grid search on the regions of hyperparameter space that seem to be important. because again, we can't afford, in reality, an exhaustive grid search. And then during this process, what you can constantly be doing is evaluating the loss curves, or like the learning curves. And usually the plots for these, what you'll want to do in setting these up is you'll want to look at kind of two separate plots. So on the left-hand side, one good plot is to look at training step on the x-axis, or epoch, training epoch on the x-axis, and then on the y-axis to look at the loss that your model is being trained according to. And if you plot the individual batch loss as, like, let's say in this case it's blue circles, blue scatter points, and then also the mean of the loss across some sliding window, what you can get a sense of is the trend for what the mean of the loss is doing, but also the variance over time. And so usually what you'll want to see is like that the variance starts to converge, but also the mean is converging downward. So in addition to that, then a second plot which is useful is at the same time during training to evaluate the, like, let's say the final accuracy, like the final metric that you really care about. So on the training set, and then also on the held out validation set. And so that can be then a way to detect overfitting or underfitting. So it'd be overfitting in the case maybe where your training loss or your training accuracy starts to really diverge, and maybe your validation loss would even start to decrease. So a few common interpretations from these types of curves that you would see. So if you start to see your training loss maybe start on a plateau, that might indicate that you have a bad initialization, or your initial learning rate is far too small. If you see your training loss plateau below what you would expect it to if it was performing with a high accuracy, or below what maybe other published results from the same data sets have seen, then potentially then maybe you should add like a learning rate decay. So maybe either like step down your learning rate or add the cosine learning rate decay. In addition, if you see something like where your loss was initially decreasing, and then maybe you did try a stepped learning rate decay, and now it's plateaued, then maybe you stepped your learning rate down too early. So maybe you could have still benefited from some convergence that was happening before the decay. If both, like a really good plot, this should make you really happy if you see this, is like where you see both the validation accuracy and the training accuracy moving upward with some discrepancy between the two. This is good. This just means keep training. Everything is going well. Your validation accuracy is improving. If you see a plot like this, where your training accuracy is now diverging from your validation accuracy, then this is overfitting. So you'll want to either add more regularization, more augmentation, increase the size of your data set, all those things we talked about to avoid overfitting. Kind of a counterintuitive one is maybe one that looks like this, where let's say like your training accuracy and your validation accuracy are very close to each other. Maybe they're going up, but they're not super accurate yet. Like they're not maybe like 100% accuracy or 90% accuracy, picking some high numbers out of the hat. This might be indicating underfitting. So it's maybe possible that if you were to keep doing this, like both would now converge together to some value that's below what an actual more well-fitting model could ultimately achieve. So in this case, you might want to increase the size of your model, try a larger learning rate, try to essentially add more more model complexity to the model architecture. And so at that point then, now it's just like kind of iterative refinement. So using now like that final like step 5, where you'll like once again maybe refine your hyperparameter grid search, go back to your loss curves and try inspecting them to see what you can take away. That is a way to approach tuning hyperparameters and choosing hyperparameters in the case where an exhaustive grid search is not feasible. And it probably seems like this is a lot of tuning. Like this is a lot of trial and error that you'll end up having to do. And I would say in reality that is the case, especially if you're trying to come up with a new architecture or apply an architecture on some new data set, maybe if it's a very different data set than what others have applied it to. It is a lot of trial and error. Like it is a lot, and it's more of an art than a science, this hyperparameter tuning. Maybe you could propose some new algorithm that would solve it for us, which would be great. Having said that, another useful tool to be aware of is like what's called TensorBoard. So this is one way that you can visualize a lot of different losses and a lot of different kind of like measurements internal to the network. So you can visualize like the norms of the different layer weights within your network, all in real time while your models train. So TensorBoard is embedded within TensorFlow, but also it's integrated with PyTorch. So it gives you like a web browser GUI where you can actually visualize these statistics as your model trains. You can also visualize in TensorBoard like actual like classification output or other outputs from your network in real time. Okay, so yeah, one statistic, for example, that's kind of commonly used. I don't have good intuition about why this is very beneficial or like from like a theory standpoint, but if you actually look at like the ratio of your weight update to the weight magnitude, generally for networks that are training well and like on the right track, you could say, you'll sort of expect it to see in this ballpark range. So these kind of statistics are what you'll usually see being plotted in TensorBoard and similar tools. Okay, so that covers what I wanted to get to today. So it was kind of finishing up what we were talking about on regularization, data augmentation, and then these training dynamic considerations. What I'm gonna leave in the slides, so we're not gonna go over this in next lecture, but there's a really interesting, kind of final set of slides here on model ensembling and also then transfer learning. So model ensembling is a fascinating idea which is used pretty extensively in machine learning, where it turns out that essentially combining independently trained classifiers can actually boost the final performance if you combine their decisions. There was a really kind of scientifically fascinating but also humorous article posted in EdSTEM by one of our kind of colleagues from science that looked at taking pigeons, I think it was pigeons or some bird, and using them to classify X-rays for tumors, and found that ensembling the pigeons' decisions was better than human performance on X-ray tumor classification. So really fascinating. So if you want to check that out, it's posted on EdSTEM. And that's it for today. So next time, if I kind of skim forward, let's see, next time, maybe I'll cover just like a little bit of transfer learning. But next time we're going to talk about, okay, I'll touch like a little bit on transfer learning and then deep learning software. And that'll be it for today. Thanks for coming.